In this video, I will be going over the section 6.3 notes, which are going to talk about square root functions. The reason why we're talking about square root functions today is this. All the way back in chapter 4 and chapter 5, the main focus was x squared. And the reason why we talked a lot about x squared is because functions involving x squared can be factored. Possibly we can use square roots to solve them or quadratic formula, and we know their graphs are pretty consistent because they're always parabolas. Well, recently we have been talking about inverses, and the inverse of a square is a square root. So these are inverses. And so a lot of what you're going to see today is going to parallel graphing parabolas because we can just switch things around since they're inverses. So the one thing that I want to start with is the basic domain and range of a square root. And I want to make it clear that there's no plus or minus in front of this square root. And the reason why there's no plus or minus is because if I were to draw the other part of this graph that represents the minus, it wouldn't pass the vertical line test. So we're just assuming that it's only part of the graph, so that way we can classify it as a function. But in this picture, the domain is x such that x is greater than or equal to 0, and the range is y such that y is also greater than or equal to 0. And we're going to see this change. So for example, instead of the graph going up, the graph might go down, so that might affect the way that the range is. Or the graph might actually go left instead of right. That will affect the domain. But this is the basic domain and range of the parent function, and that is f of x equals the square root of x. And so we have some idea on how to find the domain of square roots without looking at their graphs. So let's take a moment to remind ourselves that for number 1, to find the domain of this square root function, I would take x minus 3 and say that it's greater than or equal to 0, and that would give me x is greater than or equal to 3. So then the domain would be x such that x is greater than or equal to 3. So the graph of this one has been moved slightly to the right. Notice that this is now a 3 instead of a 0. But how do I find the range? Okay, so the way that the range is going to work is you're going to take this 3 that you just found and plug it back in. So that would be 3 minus 3, which is 0. Let me write this down. So you're going to take this 3, plug it back in. 3 minus 3 is 0. And the square root of 0 is 0. And that 0 is going to represent the y value for the range. So I'm going to say y is greater than or equal to 0. This will make a little bit more sense after we do the next example. So for problem number 2, let me find the domain first. I have x plus 6 is greater than or equal to 0. So that is x is greater than or equal to negative 6. So the domain would be x such that x is greater than or equal to negative 6. But now I'm going to take that negative 6 and plug it in. And the same thing is going to happen over and over again when you do this. You're always going to get that 0 underneath the square root. Because if you plug in negative 6 here, negative 6 plus 6 is 0. But what makes this problem different is that there is a term on the end being added. So it would be 0 plus 2. Okay, so if I plug in negative 6, I would get 0 plus 2, which is just 2, and that 2 is going to represent my range. So y such that y is greater than or equal to 2. So this is going to lead us to a little bit of a shortcut notation here. It's the value on the end. Okay, so there was no number on the end for number 1, so I used a 0, but notice that the number on the end for number 2 is a 2, so I use a 2. So you don't necessarily have to show a lot of this work here. So then for number 3, the domain is going to involve a fraction. X is greater than or equal to negative 5/3. But the range, I'm not going to show any work for this. Notice there's no number being added or subtracted on the end. So I'm going to say y such that y is greater than or equal to 0. And it has a little bit to do, and I'll talk about this here in a moment, it has a little bit to do on finding the vertex of the graph. So if I go back to the very top here, every square root function is going to have a vertex, basically where the graph starts. And the way that we're going to graph these square root functions today is we're going to find that vertex first and then plot the rest of the graph. So there are some rules that you can pay attention to when it comes to transformations of square roots. I'll hit the highlights here for you. The a value out front is going to describe if your graph is going up or if your graph is going down. So it says here in this first bullet point, if a is less than 0, if it's negative, the graph is reflected across the x-axis and it's basically just going to go down. Okay, so if your a value is positive, the graph goes up. If your a value is negative, it goes down. Now, if you take the absolute value of a, okay, the graph can be stretched vertically, meaning if a is greater than 1, it's going to be stretched out a little bit wider. But if it's a value between 0 and 1, then it's going to be more narrow. It's going to be compressed. Okay, so if you want to make some notes here, you definitely can. But this does a good job of noting whether it's going to be stretched or compressed. But I do like the fact that here, for this first bullet point, I would write the word down. The graph's going to go down. But the graph can also be translated left or right, and that's going to be with the h value. And then it can also be translated up or down, and that's going to be with the k value. But the way that I'm going to show you how to graph these, you don't really need to memorize this information necessarily. Maybe the a value is important to know, but the h and the k value, we're going to kind of incorporate that into our graph. So the first thing that we're going to do for 4, 5, and 6 is we're going to find the vertex. And the vertex is going to be very similar to finding the domain or the range of the graph. So to find the vertex of this graph, I'm going to take the 3x, I'm going to take the term underneath, and I'm just going to set it equal to 0. And if you divide by 3, you get an x value of 0. The number on the end, so this corresponds to the range, the number on the end is the y value of that vertex. So this is your h and this is your k from the above formula or the model. So h is found in a similar fashion to the domain, and k is found in a similar fashion to the range. So I'm going to go ahead and plot the point 0, 0. So I'm actually going to take a moment, and I'm just going to find all of the vertices here. So let me go ahead and go to number 5. Number 5, the vertex should be, so if I take x plus 4 and set it equal to 0, I get x equals negative 4. And once again, there's no number on the end of this function, so that is a 0. And the vertex for number 6, if this is x minus 3, I set that equal to 0, so that would be x equals 3. So the vertex here is 3, comma, and this time I get a y value that's not 0, it's 2. So that's your first step in all these problems, find the vertex. And the vertex is found in a very similar fashion to the domain and the range. So if you wanted to, you can go ahead and fill out the domain and range at this point, but I actually think it's a little easier to graph it first, then go back and write out your domain and range just to verify that you've got everything correct. So I'm going to move on to the graph next, and the graphs here are just going to require making a quick XY table. We know that if I put in the point 0 for x, I would get back the point 0 for y. Like I already know that information. The problem is if I use an x value of 1 and I plug that in, 3 times 1 is 3, and that's going to give me the square root of 3, which I don't really want to graph the square root of 3. I want something that's more of a whole number. So then, just in your mind, I would test 2. 3 times 2 is 6. Well, I don't want to take the square root of 6. But if I test an x value of 3, 3 times 3 is 9. The square root of 9 is 3. So just doing some mental math here, the next number I would test would be 4. 3 times 4 is 12. I don't want that. It's not a perfect square. If I plug in 5, it would be 15. 6 would be 18. 7 would be 21. 8 would be 24. So I'm trying to find multiples of 3 that are perfect squares. And the next number that shows up is 12. 3 times 12 is 36, and the square root of 36 is 6. So besides the one that had the square root, I'm also going to graph the point 3, 3, and I'm going to plot the point 12, 6, which is going to go off my graph slightly. And then I go ahead and make my ray, my curve. So now that I have my graph, I can see that the graph is going to the right, so the domain would be x such that x is greater than or equal to, and it's just the 0 that you found earlier. And the graph is also going up, so the range would be y such that y is greater than or equal to 0 as well. So these two numbers are going to match your vertex. All right, so for problem number 5, kind of same thing. I would need to make an xy table here. And we know for certain that -4, 0 is a point on this graph. But I don't want to write down any other x values until I find one that works out to be a perfect square. So if I plug in -3, -3 plus 4, -3 plus 4 is 1, so that's a perfect square. So let's go ahead and take care of that. So -3 plus 4 is 1, the square root of 1 is 1, and 1 times a half is a half. I can graph a half. All right, so -2, -2 plus 4 is 2. I don't want to take the square root of 2. -1 would give me 3. 0 is going to work. Okay, so if I plug in 0, 0 plus 4 is 4. The square root of 4 is 2. Half of 2 is 1. And I think the one that's going to work after this is going to be 12. 12 plus 4 is 16. The square root of 16 is 4. Half of 4 is 2. So there's my graph. And I want you to note that this one is kind of compressed. It's kind of squished. And that's because of this A value. That value falls into this last bullet point up here. It is compressed vertically. And so the domain would be x such that it goes to the right. So x is greater than or equal to -4. The range y such that y is greater than or equal to 0. All right, so just a little bit more here with number 6. Number 6, we have to make an xy table. And just to kind of speed things up here, we know we have the point 3, 2. The next one that I would use, 4 would also work. So 4 minus 3 is 1. The square root of 1 is 1. -2 times 1 is -2. -2 plus 2 is 0. The next one that would work would be 7. 7 minus 3 is 4. The square root of 4 is 2. -2 times 2 is -4. -4 plus 2 is -2. And then I think that's it. I think anything else might not fit on the graph. All right, so let me go ahead and plot this. So I've got 3, 2, I've got 4, 0, and then I've got 7, negative 2. This one's going to go down, and the reason why it goes down is because this a value is negative, but the absolute value of negative 2 is 2, so this one is stretched out a little bit more compared to the previous one. So if anything from the tables above that I would pay close attention to, it's the information about the a term. Very important. So now I'm going to go back and talk about the domain. It goes to the right still, so the domain here would be x such that x is greater than or equal to. So let me change that real fast. So greater than or equal to, and then the number I'm going to use here is 3. And then the range, this one changes. This is probably what I meant to write. Y is, since it's going down, less than or equal to 2. So a couple things to pay attention to, but specifically for this last problem, the graph is going down because the a value is negative. That forces the range to change to less than or equal to. There's your video for today.